Good evening, this is Jay Yablon, and let's talk about physics. In 1957, John Archibald Wheeler wrote a seminal paper called On the Nature of Quantum Geometrodynamics. It was in Annals of Physics 2, 604 to 614 is the citation. We'll have that on the website. That paper is now 65 years old. And what I'd like to do tonight is a retrospective on the main ideas that Wheeler had in that paper from 65 years ago, hence the title of tonight's talk, Quantum Geometrodynamics, a 65-year retrospective. We're going to go through what Wheeler talked about back in 1957, and then we will update it with the things that we have learned since then. And in particular, our goal is to try to understand what aspects of the presentation of the development that Wheeler had in that paper still applies to the fundamental question we face today of finding a unified theory that puts together general relativity and quantum mechanics. And that is the overarching theme of the series of talks that we'll be putting together and posting in the coming days and weeks. Let's start very simply. Let's go to Newton's law of gravitation. We'll write that in terms of the potential energy between two interacting masses, and that's going to be minus the Newton gravitational constant times big M times little m. That's usually the big mass of a planet. That's usually a little mass like ourselves. And all of that taken over r, the negative sign for the gravitational potential energies. We'll come back to this relationship a little bit later, but for the moment, let's focus particularly on the denominator in that relationship. So let's take the r back out. Let's take the e back out. Let's even take the minus sign back out. And instead of having two masses here, let's just take two equal masses and make this denominator gm squared. And we are going to then, this has the same physical dimensions as h bar c. H bar being the reduced Planck constant, c being the speed of light. And what Wheeler pointed out in that paper, this may have been known previously, but he really ran with it, is that we can define a mass as the Planck mask. So we're going to put a P over here for that. And we're going to define it as h bar c. Again, we're going to start by just talking about some definitions. And if you actually look at the numerical magnitude of the constant h bar c, that is equal to 0.197 approximately GeV times Fermi. Hc as well as g times a mass squared has dimensions of energy times length. And that's important. We're coming back to this a number of times. The constant hc itself has dimensions of energy times length, as does the mass g, or the gravitational constant times a mass squared. So Planck mass is defined according to this formula. Very easy from there to simply find out, to isolate that, and we see that the Planck mass itself is going to be the square root of h bar c over g. So very simple starting point. What we're really talking about here, I should have given this a broader perspective. There are three fundamental constants we're going to start with: g, h bar, and c, and we're going to create a Planck mass, and we're going to create a Planck length. We're going to define them, and then we're going to talk about the physics that involves these sorts of things, or that may involve these sorts of things. So this gives you the Planck mass. Knowing that h bar c is always in dimensions of energy times length, the other thing that we can do is we define a Planck length. And that is simply going to be a Planck length. We'll write it this way. And we're going to define that as, well, if we have HC is, H bar C is in dimensions of energy times length, we're going to take HC and we're going to divide it by the Planck energy, which is simply, the Planck energy is going to be the Planck mass times c squared, and the result that we're going to get for that is going to be, and I have this memorized, but let me make sure I don't mistranscribe it, h bar g over c cubed, and that's the Planck length, and that is on the order of 1.62 times 10 to the minus 35th meters. Okay, so we have those two quantities. What else can we do? We can, of course, divide this length by c, and we can get a Planck time. Not necessary to really do that here. Let's now go over to Boltzmann's constant. Boltzmann's constant times a temperature, and this is all dimensional analysis so far. We're not talking about any physics, we're just talking about certain quantities that you can define from the fundamental constants h, c, g, and Boltzmann's constant. We can define a Planck temperature. Let's call that Planck temperature, and that's going to simply be the Planck energy, which is this guy times c squared, divided by the Boltzmann constant. And that temperature is on the order of 1.42 times 10 to the 32nd Kelvin. So that's pretty hot. That's, 10, 15, even 20 orders of magnitude hotter than the hottest stars, and it's certainly a lot hotter than our sun. But that's the Planck temperature that we're defining. We could do some other things. We can define a Planck density. We'll call that rho. We'll put a Planck subscript on it, and that's going to be the Planck mass over the Planck mass over the Planck length cubed. There, and that is going to be c to the 5th over h bar g squared, and we don't have to write on all the numbers, but the main thing to keep in mind is that this comes out to be 5.16 times 10 to the 96th kilogram per cubed meter. You can see the 9 here. 10 isn't too good. Let's just fix that a little bit. Okay, so obviously an extremely, extremely high density. The other thing we can do, for example, is we can take the constant from Einstein's equation, which is kappa equals 8 pi times Newton's constant over c to the 4th. And one quantity that we can also form is a string length. It's the length of strings that show up in string theories. And we will call this L. We'll put an S on it for the string length. And that happens to be equal to h bar times c times kappa. And that, when the factor of 8 pi gets into this thing, that is simply a square root of 8 pi times the Planck length. And that is, if you just take the square root of 8 pi, that's just over 5 times, 5.01 times the Planck length. So those are the basic quantities. The other quantity that we're going to define is the Schwarzschild radius of a Planck mask. And again, these are all definitions. We're going to come to the physics of these quantities in a moment, or to how Wheeler discussed the physics of these quantities. So we're going to do the Schwarzschild radius, and the Schwarzschild radius of any mass is going to be 2, oops, forgot the 2 here, 2gm over c squared. And in the event that the mass is the Planck length, then the Schwarzschild radius of this Planck mass, so we'll put a P on each of these, is going to be, turns out to be simply twice the Planck length. And you can define a Planck diameter, which is just going to be twice the radius. So we can do the Planck diameter is equal to 4 times the Planck length. And we notice, for future reference, we will come back to this, that the string length defined using kappa is 5.01, or about 5 times the Planck length. So it is larger than the Schwarzschild diameter. We should put an S in here. The Schwarzschild diameter of a Planck mass by a factor of what turns out to be square root of pi over 2. And that is equal to 1.253. So these are just a few numbers to have in mind. And I think that's probably all the numbers that we need for now. So now let's talk about some of the physics that goes into that Wheeler extracted from all of this. Let us suppose that, and this is the geometrodynamic vacuum, and we're gonna travel back to 1957. There's a lot of things that were not known back then. Yang-Mills theory, which was non-abelian gauge theory involving non-commuting operators, was 3 years old at the time. I happen to have also been that 3 years old at the time. But so that was, that was brand new at the time. The developments that we saw in the 1960s and 70s, of course, were a decade off at that time. We did not have electroweak theory. We were making some progress on weak interaction theory, but again, you only had Yang-Mills, and it was SU2 from Yang-Mills that fit the weak interaction, along with some parity violations, which surprised everybody initially, but turned out to be extremely critical. So what we really knew about at the time was gravity. We, of course, had Newton for several centuries, and we had general relativity at that point for 40 years or so. And we knew about electrodynamics from Maxwell, and Hermann Weyl had clued us into the fact a couple of decades prior to the 50s that electromagnetism was a gauge theory, and he exposited what that all meant. And so Yang-Mills later on was able to get used in combination with gauge theory, and then you get to the 1970s where you truly had a handle on strong interactions. Electroweak interactions developed late 60s, early 70s. But those weren't there yet in the 1950s. So what did Wheeler do? And of course, something that we're going to come to later on, which will be very important in all of these topics, are black hole thermodynamics. We did not have a clue and would not know until 1972 from Bekenstein that black holes had entropy. Several years later from Hawking that this meant that they radiated a temperature. We're going to come to all of this. And later on in the early 80s, Bekenstein generalized all of this to find the Bekenstein bound, which is a very critical relationship as well. So we're back in the 1950s, and Wheeler has, sort of started with all these numbers, and now the question is this. Suppose I take two Planck masses, two fluctuations in the vacuum that we will call the gravitational quantum geometrodynamic vacuum. And we take these two fluctuations, and here's a first Planck mass over here, and here's a second Planck mass over here. And, we're calling these a fluctuation. And the distance between those fluctuations is the Planck length. So what happens? I put these two fluctuations together. They're really close to each other. Now the Planck mass, which I should have written down earlier, is 2.18 times 10 to the minus 8th kilogram. So, that's not an extremely massive body. However, when you're putting them this close, so the Planck length, which is 10 to the minus 35th meters, 1.62 times that, those are very close. And in particular, the important thing to keep in mind is that a Planck mass has a Schwarzschild radius, which is equal to twice the Planck length. So if you've got these two masses here, the Schwarzschild radius of this mass is going to be, out here, and the Schwarzschild radius of this mass is going to be out here. So they're inside of one another's Schwarzschild radii. And so Wheeler recognized that these fluctuations, if they are this densely packed, and the density of the packing happens to be the Planck density, which is an incredibly dense 10 to the 96th going on 10 to the 97th kilogram per meter cubed. These things are going to be black holes. And back in the day, those were referred to as wormholes because they were ultra tiny black holes. They were not the size of the collapsed stars that we see cosmologically, that we tend to think of a lot when we talk about black holes. And let's say this, I'm going to ask people who work in black hole theory and have done a lot of thinking about it. Let's reset, because you're probably thinking an awful lot about cosmological scale black holes. And what I want you to do here is, let's go to the other end of the spectrum. Let's think about what happens when you're talking about extremely tiny black holes of this sort on this scale. Well, okay, first question, and this goes back to sort of what I started with and erased here, the gravitational potential energy of interaction between those is a negative energy, and that's going to be E is equal to minus G, and since it's two Planck masses, it's going to be Planck mass squared, and the separation is the Planck length. So if you take two of these masses and you separate them out by the Planck length, this is going to be your gravitational energy, and if you calculate it out, and we won't do it, but it's simple to do, you're going to find out that this is equal to minus the Planck energy. So what do we have here? We've got a Planck energy, and in here we've got a minus, we'll use the mass right now, all you need is c squared to get to that. And you've got a minus Planck energy. So there's an offset which is exactly equal to the positive Planck energy. And of course now, we're starting with two of these and we're looking at a single Planck mass interaction between those gravitationally. And so now let's generalize that. Let's put a whole bunch of these fluctuations in here. And let's make this a statistical problem. So, it's not that we're going to have a whole bunch of Planck masses lined up like a crystal lattice or something of that sort, or maybe you have a pyramid structure that gives you the tightest packing that you can. Then you'll get factors of an equilateral triangle that are going to, amplify your numbers a little bit. But let's just make these fluctuations, and let's say that the average fluctuation is the Planck mass, and the average separation is the Planck length, and therefore the average interaction energy of gravitation is minus the Planck mass when taken as a mass. So you have all of these things, and if you look at the whole thing, this is going to be statistical, and of course we want to know how you describe the statistics of all of this. But the most important thing is that the gravitational interaction cancels out the masses that you're starting with. So if you just replicate this and fill the blackboard and fill the room and fill everything in the universe with these fluctuations, what you're going to have, even though when you look up really close, is you're going to have a huge density of 10 to the 10 to the 96 kilogram per meter cubed. When you telescope out a little bit and look at some region of this thing, maybe go out 10 or 20 or 100 times the Planck length, the initial thought, if you're looking at this classically in terms of the gravitational interaction here, is that you're going to have a vacuum. You're going to have, and I'm putting quotes around vacuum because we're going to talk in a moment about what it really means to call this a vacuum. But you're going to have your gravitational energies, if you take them classically as negative potential energies, they're going to cancel out the fluctuations on average. So you're going to have a vacuum, and this is what Wheeler referred to as the geometric or the quantum geometrodynamic vacuum. And he pointed out exactly this, the cancellation that you have from gravitational energies. Again, no recognition at the time because we didn't know for another 20 years or so that black holes, which means these guys sitting inside the vacuum, are going to be emitting Hawking radiation and are going to have entropy and are going to have a black hole spectrum, just like the spectrum I have up here, which is a simplified rendition of the Planck spectrum. I'll come back to that in a moment. We didn't know that yet for another 25 years or 20 years. So we're looking at these wormholes and we're looking at these black holes and we're looking at these cancellations. Now, there are two ways that you can understand this cancellation of energies through the gravitational interactions. One way to do this is exactly what I just said. Positive energies, negative energies of the same size. Replicate this thing enough and you're going to, over any expanse, have a vacuum. Then you have a problem that needs to be solved, and that goes under a number of names, but it is the Baryon asymmetry problem. That's one of the ways of couching this thing. And it basically says, okay, well, if these things are really dense, like this dense, 10 to the 96 kilogram per meter cubed dense, if these things are really dense locally, when I telescope out, suddenly I have a zero, but in the observed universe, there is a slight density of matter over antimatter, of baryons over antibaryons. And if you actually take the numbers, you will find, actually, if you use the cosmological constant, we're not saying that the baryon energy comes from the cosmological constant. We're just using it as a point of reference to give us orders of magnitude. That would be 590.96 times 10 to the minus 27th kilograms per cubic meter. So that's 122 orders of magnitude less dense than what you get over here. So again, we're not talking specifically about cosmological constant, but it sits in the background because you need to take this very high density, which is very localized, which becomes zero over any large scale large spatial expanse where you're considering this. And you need to whack it out of balance just a tiny bit. And how tiny is the tiny bit? You need to get it out of balance by a factor of about 1 out of 10 to the 120. So that's a tiny fluctuation or tiny deviation or a tiny break of this exact symmetry of the vacuum. So that's one way to look at it, and then you get to the problem, how do you do that? Second way to look at this is the following. Let's go to particles and antiparticles. If we go back to 1920s, 1930s, some of the early development of quantum mechanics, you had originally the Schrodinger equation, And Klein-Gordon turned that into the relativistic Schrodinger equation. And one of the things about the relativistic Schrodinger equation, let's just write it down real quickly. We can do this partial derivative sigma plus m squared c squared times some wave function. Let me mess this up. Times some wave function. Whoops, that should be here, equals 0. Let's get that out. This is not a 0, this is a phi. Okay. So this is your Klein-Gordon equation, and it's second order. And anytime you take the square root of a number, of course, you can have a positive sign in front of it or a negative sign. That's indeterminate. So that bothered Paul Dirac quite a bit. And he said to himself, I don't like these negative energy solutions. I've got an idea. Let's find a way to make this a linear equation. So what he did is he developed the gamma matrices, and we'll use the momentum in here. Pi sigma minus m. So actually, then if we go to the derivative, we're going to flip it, plus m, and we're going to have a wave function, and that's going to be 0. And so that became Dirac's idea for how to avoid the square roots and how to avoid the negative energies. But of course, what we all know happened is that these wave functions had 4 components, and 2 of the components were the non-classical two-valuedness, as Pauli called it, which we associate with intrinsic spin. But the other 2 components, the other degeneracy, turned out to still give you the particle-antiparticle problem. In the end, that problem was resolved by Feynman and Stuckelberg, who said, you're going to have to live with this. Dirac was trying to have holes and fill the holes. In the end, Feynman and Stuckelberg said, hey, negative energy particles, which happen to move backwards in time, are equivalent to positive energy antiparticles, which move forward in time. So if you're getting negative energies out of here from gravitation, and you look at this from a particle physics view, as opposed to sort of the classical gravitation that's embedded in this, then you're going to want to regard these as positive energy antiparticles. So now you have 2 masses in the vacuum, and they create a positive energy antiparticle between them. So what you're basically doing, instead of having the vacuum become 0, you're going to double up this energy density, and it's going to be twice as much, because now you're going to have a sea of particles and antiparticles. And of course, we see this all over the place. And it's well validated in experiments. Take a photon, which has energy more than twice the electron rest mass, so 0.511 MeV, double that, so you've got a little bit over 1 MeV. If you take a photon with a higher energy than that and you run it near an atom, close enough, that's going to pop out not a positive energy and a negative energy electron, but a positive energy electron and a positive energy positron, and you're going to have double that energy. So we're very accustomed in particle physics to thinking of it this way, or to thinking of this in terms of this guy being an antiparticle that still has positive energy. So if you look at this problem that way, then the Baryon asymmetry problem takes a little bit of a different route. Now, your density is this, doubled, because every one of these is going to give you an antiparticle. And then the question is, how do you get down from densities which are now 10 to the 97 kilograms per cubic meters? How do you get that down to the smaller densities, to the far smaller densities that we find on the order of 10 to the minus 27th kilogram per meter cubed, which is more than 120 orders of magnitude less dense. That goes under the guise of the cosmological constant problem, but it's all interrelated to the fact that you're starting with a vacuum that makes use of the Planck mass and that's separated by the Planck glass, separated by the Planck length, gives you these gravitational interaction energies. One way or another, you have to get down from these extreme densities that are native to the vacuum, and you have to get down more than 120 orders of magnitude to explain what we actually see. One of the ways that will be important, not in this lecture or in this talk, but as we go forward, is this guy up here. And the fact that this is a reciprocity. It's a form of reciprocity relationship. We're going to talk about this quite a lot. It's tied in with the uncertainty principle. Again, not the main topic of this talk, but we will talk about that quite a bit when we come to future. The main thing to think about, and this is to put in the back of your mind, is we can take this number and we can think of this as a rough way of telling us what we need to do to observe spatial resolutions microscopically on certain scales. Some people refer to this, I kind of like the terms, Heisenberg's microscope. It basically says this. It says HC is a constant, and it's, let's call it 0.2 GeV times Fermi. If I decide that I want to be able to observe a spatial resolution of 0.197 Fermi, 1 Fermi being 10 to the minus 15 meters, then I have to supply 1 GeV of energy. If, on the other hand, I'm happy with only observing resolutions down to 1 Fermi, then I only have to provide 0.197 GeVs. And if I provide a lot less energy, then I'm going to have much wider spatial resolution, so I'm not going to see as much. My microscope won't be as powerful. And if I provide more energy, then I'm going to see tighter. I think one of the ways that we're going to want to think about getting from 10 to the 96 down through 120 orders of magnitude involves being very attentive to the spatial resolution of our observations, and not only in terms of an energy that you supply, which is in this formula, but when we go to temperatures, we want to think about temperature as a different form of probing into nature. In a particle accelerator, we take particles, we accelerate them, we collide them together, we do forensic analysis of the debris, and we figure out what the heck we think happened as a result of those collisions. And that's our microscope into particles, into molecules, into atoms, into nuclei, into the neutrons and protons. And if you really get deep with your scattering, then into the hadronic, or the quark structure inside the hadrons. So all of that is, energy-based probes. And we're very familiar with that in the particle physics arena. But we're also going to want to think about temperature-based probes, and how when you heat up a black body or when you heat something up, you're doing something to that which is giving you higher energies of the photons emitted. And you can think of that, if you will, since those photons have shorter wavelengths, the more you heat things up, as something that gives you deeper spatial resolution, but in the temperature domain. So, okay, that's the background for the vacuum. Now let's fast forward a little bit and let's go to the 1970s. And if I can find where I put my marker, we are going to talk a little bit about black holes and their radiation spectrum. I think I still have a little room here. So Okay, let's go to, well, let's do a couple things here. Since this series of talks is about those key elements of known physics which are likely to play an important role in unification of general relativity and quantum mechanics, the first candidate which I would like to propose for that is the set of discoveries by Bekenstein and Hawking in the 1970s, which said that black holes have entropy and that they emit the radiation spectrum of a black body. Why the link? Really very simple if you think about it. Let's go back to 1901. Here is Max Planck, who's taking the Rayleigh-Jeans law, which was observed at large wavelength and low energy for that part of the photon spectrum over here. This is a wavelength, or wavelength over the peak. I actually put the peak at 1, just to make it easy. You can do that by reparametering Planck's law, parameterizing Planck's law. I may show that in another talk. I don't need to do that here. Let's keep it simple. So the way Planck's law works is that there's always a peak, and if you reparameterize it, you can give it a dimensionless height of 1, and then when you raise the temperature, you're just scaling your axes, but the graph is always going to be the same, and it's really the Wien displacement law which describes that, and I may write that down in a moment, but let me see if we really need to have that on there. So Planck in 1901 discovers that the long wavelength from Rayleigh-Jeans and the short wavelength relationship, which also was discovered by Wien, that these two didn't really match, but if you put them together, you could get this curve, which he described, and this is his curve, or this is Planck's law in detail, expressed in terms of wavelength as a function of wavelength and temperature. And just look it up. I don't have to go into that here. And one of the key pieces, however, of course, is that he finds out that the energies inside of whatever is fluctuating are going to be in times Planck's constant, which is 2 pi times the reduced number that we're using here, times a frequently. Most important thing here is n. Quantization of energy. Einstein took that in 1905 with the photoelectric effect, and really generalized what was going on. Planck kind of for a few years thought, oh, this is just a mathematical gimmick I'm using to get the right curve, and Einstein said, no, buddy, that's not how it's working. The energy is actually quantized, and we went from there, and this started the quantum revolution. And you go into the 20s and 30s, and all of a sudden you're getting canonical commutators and the Heisenberg matrices, and those are ways of accounting for this quantization of energy. And those lead to the uncertainty principle, and those lead to spatial measurement resolution limitations, where you're trading off the energy you apply for the spatial resolution you observe. Again, just like we were talking about here. What really happens is when you're talking about those terms in terms of the uncertainty principle, you also have a factor of 1/2 that shows up in these equations, and we'll come back to those too. So why is Bekenstein-Hawking likely, very likely, I would say, to have a central role in the unification of general relativity and quantum mechanics? Because Planck predicts this, or Planck quantifies this in 1901 and does it by finding quantization, and that kicks off a revolution that in many ways is still continuing to this day, and in many ways it will continue until we finally figure out how quantum general relativity fit together. because we don't know that. And because that is an outstanding problem, in many ways, the quantum revolution does continue to this day. But it certainly has a storied history into the 1930s, into Copenhagen, and the interpretation that emerged from there. So you've got Planck in 1901. Now, let's switch over to general relativity. This is all quantum with a capital Q. Let's switch over to general relativity. Well, general relativity has these black holes, and Schwarzschild had his solution within a year or so after the general theory came out in 1915. I think Schwarzschild was 1916, 17, somewhere in there. But that came out very quick, and people figured out pretty quickly that there was a singularity, and if you took all of a mass, a gravitational mass, and stuffed it inside of its Schwarzschild radius that we have over here, that you would end up having this black hole. And for a long time, there were these discussions about, well, what does that really mean to have a black hole? And could anything get out of a black hole? And Hawking made some bets involving black holes having hair, and all of these things went on. But the place where things really important happen is in the 1970s, because black holes were discovered to not really be black. They did emit something. And what they emitted was Planck radiation. So if you have general relativity totally by itself that predicts black holes, and then in the 1970s, you discover that those black holes, that's my clock, excuse it, if you discover in the 1970s that these black holes that come out of general relativity are emitting a Planck spectrum, which is the very heart of what leads to quantum mechanics, there's a connection there. That's not just coincidence. Something that is uniquely general relativistic. Without general relativity, you wouldn't have black holes. And once you find out that those black holes innately emit a spectrum that is a black body spectrum, that is quintessential quantum mechanical, now all of a sudden those two things are hanging together. And that's important. Let's briefly review just a little bit of that. And I think that could get us to the end of where we are in this first talk. The first relationship, which was Bekenstein in 1972, is this. It's that the entropy of a black hole is equal to, I want to again make sure I get this stuff down correctly, is equal to Boltzmann's constant, of course, that gives you your dimensional balance, times the area, the Schwarzschild area of the black hole, divided by 4 times the Planck length squared. And you've got area over length squared, that keeps your dimensional balance, and of course the Schwarzschild area is 4 pi times the radius squared. So this is the first thing that Bekenstein, that's found in this relationship. Black holes have this area. And of course, we know all sorts of things about entropy, most important of which is that for closed system, it doesn't decrease. You know, you can get an equilibrium system where it stays the same. You can go into non-equilibrium where it's going to increase. Again, won't get into all of those things right now in detail, but you have this coming out of Bekenstein. By the way, while we're at this is an interesting point. Holographic principle. 'T Hooft is the one who first identified this, but it's really very simple. Think about entropy. Entropy is often thought of as it's the number of microstates, or it's a logarithm of the number of microstates of a system. It can be thought of and is often talked about in terms of the information of a system. But think about this. You receive a box from the mailman. And let's just say, for hypothetical purposes, your box that just came, open the box, there's a round box. We assume that the content of what is inside that box and all the information, I want to see what's in this box that I'm getting for my birthday or whatever it is, we assume that it's going to be proportional to the volume of that box. And lo and behold, the black hole has an entropy, but the entropy is not proportional to the volume of that box. It's proportional to the area of that box. That's a strange thing, and that's what, to Hooke called a holograph, and there are a lot of people who are studying holography, and it's really due to the fact that you have the radius squared. So let's do a real simple calculation. Let's do one of the most elementary differential calculus calculations you're ever going to want to do. Okay, I'm going to take y equals x squared. Okay, x squared is your substitute here for the radius. Okay, so dy is equal to 2x dx, and therefore what I can do is I can say 1/2 is equal to dx over dy times x. Did I get that right? Okay, that's your basic calculation. You can represent that relationship in that form. And you can take a factor of half, and that is the representation of the fact that y equals x squared. But let's erase this off, and let's take the black hole and let's use that instead. So that's the basic relationship, but the relationship that I really want to write down is this. 1/2, the number 1/2 is equal to the black hole entropy over d black hole entropy times delta Schwarzschild radius over Schwarzschild radius. Okay, that is a way of writing 1/2, and it's a way that uses the y equals x squared. It's just a fancier way of doing it. But what's important is that this relationship captures the holograph. This is another way of saying that the black hole is a holograph, that its entropy is proportional to its surface area. 1/2 equals that. Why do we want to do it that way? Because the factor of 1/2 becomes your mathematical encoding, if you will, of this holograph. Now you take this 1/2 and you trace it around and you see what other equations it shows up in, and if the 1/2 in your equation comes out of this relationship, then wherever the 1/2 travels, it's carrying the holograph with it in a nice little suitcase, and you can unpack it. And that's why I mentioned the factor of 1/2 here, because one of the things we're going to show in some of the later talks is that the factor of 1/2 that you get out of the black hole holograph, this is a black hole, this is a general relativistic object, happens to be traceable to the same factor of 1/2 that shows up in the uncertainty principle, which is central to quantum mechanics. So now you've got a link right through the holographic principle between a general relativistic holograph and an uncertainty relationship in quantum mechanics. But again, that's not this talk, that's a couple talks down. There's a lot more development I need to show you before we can get to that point. So that is where Bekenstein starts out in the early 1970s. And then a few years later, Hawking says, well, if you've got an entropy, let's analyze this closely. And what Hawking ends up finding, let's make sure I get this correct, is that the temperature, the black body temperature of a black hole, I'll put the cap on the left side, is going to be equal to h bar times c cubed all over 8 pi g times the mass of the black hole. And there you go. That's your spectrum. Now, let's take this a little bit further, okay? You're here. The black hole has a temperature. This is its temperature. It emits a Planck radiation spectrum. Now we got to the question from back here of the statistics. I've got these two Planck masses. They're separated by the Planck length, but it's not exact. This is the average mass. This is the average separation. It's all fluctuating. It's a big stew. And so how do we describe these statistics of what's going on in this vacuum? Well, the temperature gives us an easy way to do that, because once you have a temperature, you have a system with lots and lots of degrees of freedom, such as this system that's got all these fluctuations going on. So you have the ability now, if we are going to take the mass here and make it the Planck mass, then that is going to be the temperature of the vacuum. And I'm going to put a V there. And if you compare that to the Planck temperature, I didn't write it out fully, but in fact, this temperature here in the vacuum is 1 over 8 pi times the Planck temperature. So it's a little smaller than the Planck temperature. It's reduced by the factor of 8 pi from Einstein's equation right in there. But now you have your statistics, because once I put a temperature on the vacuum, you've got something to work from. And in particular, you know that that's the spectrum that's coming out of the vacuum. Final thing is Bekenstein, once again, returns to the scene of what he did here. He has additional information from Hawking. And in the early 1980s, he says, let's take this bound, or let's take this entropy relationship, and let's try to generalize it to any system which has a particular radius r and a particular energy E. And let's see if we can figure out the entropy. And what he finds is the relationship known as Bekenstein's bound. And that says that the energy is, or excuse me, the entropy is always less than or equal to, I'm going to put the K from Boltzmann here, that gives you the dimensional balance. Then we're going to have 2 pi, the radius of the system, the energy of the system, over h bar c. And this is a generalized bound. And if you take the radius and make it a Schwarzschild radius, and you take the energy and you make it a black hole energy and substitute those numbers in, and you make this equality an equal sign, this equal sign shouldn't be here, okay? If you make the equality an equal sign, you end up reproducing this relationship. So this relationship, used as an equality with a Schwarzschild radius, with a black hole energy, gives you that relationship. And this is the generalization, and black holes are entropically saturated. So, one final point, and then I think we can close up and maybe preview what we'll do the next time through. Let's take Bekenstein's bound, and let's just do some 8th grade algebra and rewrite it. And what I'm going to do with Bekenstein's bound is I'm going to do this. I'm going to write the exact same equation, energy times radius, and that is going to be greater than or equal to S over pi times the Boltzmann constant times 1/2 h bar c. Okay? Do the basic algebra. This is another way of stating this. But when you look at Bekenstein's bound from this viewpoint, what do we have? Go back to here. In fact, let me put in one other relationship that I haven't written down. This relationship we talked about up here, which gives you spatial reciprocity based on the energy you apply. Or, to put it a different way, if I'm looking at the space and I am seeing closer and closer in on the space, then the energy uncertainty or the energy fluctuations grow larger. But the relationship which you can derive from the uncertainty principle is the fact that the applied energy, which I'm going to call mu, times the delta in your radar resolution is greater than or equal to 1/2. This is very good. H bar C. Okay. I hope you can see the 1/2. This is a mu. I don't know if that delta is too good, but okay. This is the measurement limitation. This is the Heisenberg microscope. You can get this from the uncertainty principle by looking at pair creation. Don't need to get into it. There's actually an article on Wiki that'll tell you how to do it if you want to see that calculation. In any event, look at this now. Same thing. Bekenstein bound says that the energy enclosed in any radius of r is always going to be greater than or equal to the same factor of 1/2 hc, but multiplied by the entropy over pi times Boltzmann's constant. This is just a dimensionless scaling factor. So you can think of this, if you think of this as an equation for fluctuations, you can think of this as an equation for entropically linked fluctuations. But the point is this: you're starting at gravitational theory with black holes. You're generalizing that to Bekenstein here. And by the way, the Bekenstein relationship also was shown by Robertson. It was shown that the Bekenstein relationship, when you take the equilibrium law of thermodynamics, reproduces the Einstein equation of general relativity as an equilibrium equation of state. So if you start here, you can derive general relativity, starting from here. If you, on the other hand, if you take this same relationship and generalize it, which involves the non-equilibrium state, and then just algebraically restructure it, all of a sudden, you've got this sort of relationship that looks an awful lot like this, which comes from the uncertainty principle, which I guess I really should put in here sooner or later, which is delta P times delta X is greater than 1/2 H bar. And of course, that's in 3 dimensions. I won't put all the Kronecker deltas in there. But you can see where all of this stuff comes together. You've got Planck quantum mechanics. You've got black holes coming out of relativity. You've got suddenly them having the exact same Planck spectrum. And then you end up getting laws here that look an awful lot like these reciprocity relationships that you get out. So final thought is this. The geometrodynamic vacuum, which we've been talking about here, right at the beginning. 65 years later, we look at that vacuum as something that is an omnipresent black hole. If you were to take a microscope, a Heisenberg microscope, but not one that works on energy, one that works on temperature, and you are to provide more and more and more and more heat so that you probe more deeply and more deeply into the vacuum, you're going to be utilizing the Wien displacement law, which I did not write down here, but the Wien displacement law is yet another reciprocity relationship. I should write that down. Let's just put it up there, get it all out there. The Wien displacement law. Rather simply, make sure I get the right one in here, is that up in this relationship, for this graph, the peak wavelength times the temperature is 2 pi h bar c over A times Boltzmann's constant, and A is a number that you calculate when you differentiate Planck's law. That's well known how to do that. Okay, 4.96. But here again, the wide displacement law, the peak here is reciprocal with temperature, and on this side you've got a constant. 2 pi h bar c, same thing here, factor of 4. A, this constant, times Boltzmann constant, you have a reciprocity. So what's happening when I'm applying temperature to a black body, of all things, which is what, a cavity? Think of it as an oven. Let's make it round. Let's put a little hole in it, and then let's make sure it doesn't emit. Pick a material that's black, so there's as little stray light as you can. Get a little hole. Heat it up. What are you heating up? You're heating up the vacuum. You're creating the outside of the oven, and you're putting heat into the inside, and that vacuum is radiating. And you're looking at the spectrum, and you're getting a spectrum like this. And the peak here is going to vary with temperature. So if I'm probing with temperature, higher temperature, the wavelengths I get to see here are much shorter. Photons are higher energy. Keep cranking up the temperature, start at the cosmic microwave radiation background for all you care. Take your oven out into space, then you really have a vacuum. You look at the spectrum, it's going to be a little over 2 degrees Kelvin. Now start heating that baby up, get it hotter and hotter and hotter. But now let's go all the way to the other end. Get it up near the Planck temperature. What is going to happen? You're going to see the photons get more and more energetic. The wavelengths are going to get shorter and shorter. Spatial reciprocity, it's another Heisenberg microscope, but now it is in the thermal domain. And in this thermal domain, when you finally are applying enough temperature to look at the vacuum up close, because you have managed to pull together billions of suns and all of their heat and get yourself up to this temperature divided by 8 pi, because of the black hole nature of that vacuum, the geometrodynamic vacuum that Wheeler had, that we're looking at 65 years later, we know that that vacuum has a very hot Planck spectrum that is this number divided by 8 pi. But when we're getting there, to get there, we're applying temperature instead of accelerating particles and banging them together. And that's what gets us to the vacuum. So now we want to look at temperature as a way that we probe into the depths of nature, into the depths of the vacuum. And when we are probing a black body, we are using temperature to probe into that vacuum. And so the reason we don't see this temperature, the reason I don't get burned, or you, just by being, is because of the fact that we are not probing with that level of temperature. It's often said that quantum mechanics, that the role of the observer is very important. What you observe depends on how you observe it in a lot of ways. That also began with the principle of special relativity. How I observe something is going to depend on my reference frame. General relativity, how I observe it, is also going to depend on the potentials and what it's going to do to the energies, whether it's going to redshift things, whether it's going to bend light. But how you observe determines what you will observe. And I think that principle, along with all of these, are likely to be important components of any eventual theory which unifies general relativity with quantum mechanics. With that, I'd like to sign off, and thank you for listening to my first talk about physics. Have a good evening.